All right, so I think we left off on problem 1652. So let's go through that problem. We're going to take A, D, F, and C. Let's take those and then go from there. And the day is the 8th. All right, so let's look at A. All of these are retrosynthesis problems. In other words, working backwards. Back to the start material. It says what diene and dienophile are needed to prepare each deal's alder product. So let's look at that real quick. Redraw it. All right. So how do we attack? Come on now, Wi-Fi. We switch. All right. So we're looking at A. And the question is, how do we go back to the starting material? What was the strategy we talked about with the retrosynthesis?
Doing the arrows backwards.
Yes. So where would you start?
The double bond.
Start at the alkene, right? That's the best place to start. So if we take that alkene, excuse me, move these arrows here, right? We're going to break this sigma bond here, and then we're going to put this here, like that, right? What that's going to give me, it's going to put a pi bond here, a pi bond here, and then one here, right? And it's going to take away the two sigma bonds here and here, right? So my diene will look like this. And then my dienophile like that.
Dr. Russell, I'm still confused as to how you get the shapes you get when you make the dienophile.
When you say the shape, what do you mean by that?
Because when I, like, if I'm practicing it and I can make the diene fine, but when it comes to the dienophile,
okay,
my shapes it doesn't come out I don't know. I think I'm just confused as to when I put the double bonds back in, my shapes come out differently, like the shape of the whole dienophile.
Yeah, so what is the dienophile is just an alkene, am I right?
Yes.
So that would be your first place to start, is just to draw a carbon-carbon double bond. You can show the carbons or not, right? For this one, you see right here where it's substituted. Let me get a different color highlighter. You see how this is substituted on one of those carbons?
Yes.
So both of those substituents are going to be on the same carbon. So that's why I drew it that way, right? And then you got to think all the way back to part one. The geometry of a alkene is trigonal.
Right.
So that's why I drew it like this and not just, I want to express the fact that sp2 carbon has a 120-degree bond angle.
Okay. Okay. I got it. Thank
Does
you.
that make sense?
Yeah, that makes more sense.
Yeah. All right. So when you get ready to draw your dienophile, if it's acyclic, just start by drawing an alkene and then come back and put the substituents on. Right. If this was a cis alkene, it would look like this, right? Where both substituents would be here. If it was trans, it would look like this, where one is on one side and one is on the other side. All right. Did that clear it up a little bit?
Yeah, I did.
Okay. All right. Let's take a look at C. C is a 3D structure, but it's not intimidating. We've seen this before. So I'm going to just redraw that. I got our oxygen up here. I have to zoom in so I can make that look halfway decent. I hate drawing these things, by the way. Boom, like that. Alkene here. And then on that, now this is a good, I'm gonna draw that ester out. All right, so where are we gonna start here? Are we gonna do something different?
No.
No.
Same strategy, different product, but same exact, come on, Russell. Same strategy. All right, we're gonna start at that alkene. We're gonna push this pair of electrons here, like that. We're gonna break this sigma bond here. And we're gonna take this pair of electrons and push them here. Right? I know it's outside, but it's still inside this, it's still pericyclic. I just don't want to try to squeeze it behind that sigma bond that's pointed up. Right. So my dienophile or my diene is going to look like this, right? I'm going to draw it in 2D. That's my diene. And then my dienophile is just a substituted alkene that has an ester on it. So I'm gonna draw the ester down here. Right, that's it. So is this is my diene, this is my dienophile. Now I have a question I want to ask. I want to kind of expound on this problem because it kind of touches on something we talked about the other day. If you look at this product, is that endo or exo?
That is
Endo.
It's endo. Good. What would the exo product look like?
It will go up.
It would be, let me just copy it. The exo will be different, right? Even though it's going to come from the same set of start materials. Exo will have that ester out here. Like that. Is that right?
Yes. I have a question.
Go ahead.
Where did the other bond, I guess, between the double bond and the CH3OOH come from? In the product of the one we just did?
Right here. You see that bond right there? So when I break this sigma bond, that's a great question. Because I know it looks weird, but when I break that sigma bond, that bond is going to disappear. Right? But the electrons are going to go there to make a pi bond between these two carbons right here. here, and here. And the ester just happens to be bonded to that other carbon. Right, and by the same token, this arrow right here means I'm breaking this bond. You see it or no?
Okay, I see it now. Thank you.
I probably should have drawn it. As a matter of fact, I'm gonna fix it. I'm gonna take I'll put the ester on the other side. That might make it. All right. Let me put those bonds back in. To the next question. All right. Good question. All right. If you were doing this reaction, would you get both endo and exo? If you did this Diels-Alder reaction on this, that's shown on this side.
Yes.
Yes. Which one is going to be more stable?
Endo.
The endo, right? Because again, with the endo, you get these secondary orbital interactions between the alkene right here and the pi system on the carbonyl, right? Those can overlap. Anytime you can get orbital overlap, that's good. It's gonna, you'll get a simultaneous energy decrease. It might not be a lot, but 1 or 2 kilocalories per mole, and on a molecular level, that's a lot, right? So anytime you get those secondary orbital interactions, it's gonna add stability to that product. Right, that's a stabilizing interaction. All right, let's do D. I'm gonna let one of y'all tackle D. Right, and the alkene that's hanging off, we're going to consider that a substituent. So what do you think? Where am I starting? Am I going to develop a new revolutionary strategy for retrosynthesis? Or am I going to do what works?
Do it work.
Do what works.
Yeah, so somebody put the arrows in. If you can annotate your screen, go ahead and put the arrows in. So we're not, the alkene that I highlighted, that's not where we're going to start. Because it won't, pushing those electrons won't open that ring up. Good, excellent. So that'll give me this. Is that right?
Yes.
Mm-hmm. Plus,
Yes.
and I'll fix that up, this. Is that right?
So are you saying, like, since you said that was this substituent,
Mm-hmm.
we basically just don't touch that?
Right, because if I start there, it's not going to pop the ring open. If I
Okay.
have a 6-member cycloalkene like I have here with a double bond in the ring, then I know that that's my Diels-Alder adduct.
Okay.
The other double bond hanging out of the ring is just a substituent. It's attached to something. In this case, it was attached to your, and this is a weird problem, but it's okay to be weird, right? This is this was my diene that we picked out. Let me fix that up. Right, and that by default, that makes this the dienophile, even though it's a conjugated diene also, but only one of the alkenes reacted. All right. So that problem, it looks weird, but again, if you follow the strategy, find the alkene that's inside the ring and start there. Right. Let's do the last one, which is it looks intimidating, but it's not. It's not intimidating at all. Let me just recreate that. That, and then this is my alkene. I think it's here. It has an anhydride on it. Make sure I get this right. Okay, I see it now. All right. Nothing special. I don't care how substituted your product is. It doesn't matter. It can be walked down just like anything else. It's all about having a strategy. If you have a strategy, you're going to apply that strategy to whatever problem that you're dealing with this particular concept. Right? Where are we starting?
Where the alkene is.
Right here.
Mm-hmm.
We pushing this pair of electrons here like that.
Yeah.
We're going to break this bond and push those electrons here. We're going to take these electrons and put them here. It's that simple, right? So I'm going to get from that. I'll do the anhydride first, maleic anhydride, which is this. This is a very, very reactive dienophile. Remember, we talked about with your dienophile, if you put an acceptor on it, it increases the reactivity. So maleic anhydride is a super, super reactive dienophile because of those two carbonyls that are conjugated with your alkene. All right, and then my starting material is just going to look like this. It was scary looking, but now it's not. It's just, look. Right, it looks scary at first, not so much afterwards, right? That's my diene, that's the dienophile. And again, the strategy is find the 6-member cycloalkene, find that alkene, find the double bond inside that 6-member ring, and start pushing the electrons from there. Because the flow of electrons for cycloaddition, it doesn't change whether it's going forward or backwards. Since it's pericyclic, the same flow of electrons going forward is going to be the same flow of electrons if you're going in reverse. If you're doing retrosynthesis, it's the same thing. Nothing changes. All right. Any questions about any of these examples? All right. So we're gonna. This is the end of the cycloaddition, and then we're going to start discussing aromatics. I already pulled a handout, but I don't have it to give to you, so I'm not going to start with that. I'll just start with some basic information about aromatic compounds. So let me start a new page of notes. I'm starting here, but I'll add a page. So, let's see. All right, so now we're gonna shift gears. I actually saw a really good video on aromatics on YouTube the other day. It was awesome. I intended to send it out, but it was too soon. I got to go back and find it, so I may send that today. Yeah, it was really good. But anyway, so when we talk about aromatic compounds, we're talking about a specific class of compounds, and there are some specific criteria that aromatic compounds have to meet. All right, so let's talk about the criteria. So I'm going to start with the perfect aromatic compound, which is benzene. All right, so benzene is considered an aromatic. The thing about benzene is, there's several things about it. Number one is really unreactive because of the stability, because it's the conjugation and the aromaticity is really, really unreactive unless you use some type of catalyst, or you just like beat the crap out of it, like using really harsh reaction conditions. It's unreactive. All of your bonds have the same length. All right. And then if you look at it from an orbital perspective, this is what really makes it special, is the fact that there is a p orbital on every carbon. Right, so we put the p orbitals in. Right, on benzene, it is. What does that mean when we talk about, when we say that there's a p orbital on every carbon? What does that mean?
That it's conjugated?
It is conjugated, but as an extension of that definition, remember we said something is fully conjugated. If it has a p orbital on every carbon. So this compound is fully conjugated, right? All the bonds are the same length, it's fully conjugated, all the p's overlap. So this is an example, benzene is an example of a 6-pi system. It's an example, just like a conjugated diene is an example of a 4-pi system. Benzene is an example of what we call a 6-pi system. All right, so with benzene, what has to happen, well, benzene kind of gives us a paradigm of what an aromatic compound should look like, right? It should be cyclic. And under classical rules, it will have to be monocyclic. But of course, there's several aromatic compounds that kind of defy that definition of monocyclic, meaning having only one ring. We're going to talk about some of those. It needs to be planar, right, or flat. And benzene is most definitely flat. And that the reason that planarity matters is for orbital overlap. Right, so if it's planar, all the p orbitals can talk to each other. Like they can all see each other and overlap with each other, right? So it needs to be cyclic, it needs to be planar. It also needs to meet what's called the Huckel rule or the 4+2 rule. Four n+2, I'm sorry, I think I said 4+2. And I'm going to explain the 4n+2 rule in a second. And it needs to be fully conjugated. Right, those are the rules that that determine whether or not a compound is aromatic. All right, and so with the 4n plus 2 rule, let me just explain that a little bit. Right, let me move this down. What that means is that the pi electrons, they have to, I've set that equal to 4n plus 2. So for benzene, 4n plus 2 would be 6. Where n is the number, I'm sorry, 6 is the number of pi electrons. So you got 3 double bonds. There are 2 pi electrons in each double bond, so 6 total. Are y'all following that?
Can you repeat that one more time?
So for the pi electrons, every double bond has 2 pi electrons, right? So if you got 3 double bonds, as we do in benzene, that means you have 6 pi electrons, right? Because each pi bond is made up of 2 electrons.
Okay, thank you.
Oh, good question, Cornetta. When you asked about the planar, I just saw that message in the chat. So as far as having a bridge is concerned, if it has a bridge that disrupts the orbital overlap, then no, right? That would take away the aromaticity because it has to be fully conjugated. But if it's substituted, it's fine, because if you put a substituent on a benzene ring, let me go over here. So Cornetta asked a question about planarity, and she said when you say planar, you mean that it shouldn't have a bridge or substituents coming out of it. So the substituent part is no problem, because benzene itself is planar. So all of your carbons are sp2 hybridized. So any substituent on that ring is going to be have that 120-degree bond angle. So it's not going to disrupt any p orbital overlap whatsoever. The p orbitals will still be able to overlap with no problem, right? If there's a bridge, then there's potential for that bridge to disrupt the aromaticity by not allowing for p orbitals to overlap. So we do something like this. Here, another one here. I need another one here. Something like that. As long as those p orbitals can still overlap, then and that's not disrupted, then a bridge won't affect the planarity either, right? It might not necessarily be flat, but the part that needs to be planar is planar, so the orbitals can still overlap. I hope that answers your question.
Yes, it did. Thank you.
All right. So back to the Huckel rule, the 4n plus 2 rule. So if I solve for n in this case is going to be 1, right? So if n is a whole number, then it meets the 4n plus 2 rule. So if n is a whole number, then the Huckel rule is satisfied. Right? If it doesn't, then the 4n plus 2 rule isn't. If the 4n plus 2 rule isn't satisfied, then one of the criteria for aromaticity is not met, then it's not aromatic. So it wouldn't be considered an aromatic compound. Right? So it has to be cyclic. And again, under classical rules, it's monocyclic, but there are aromatics that are bicyclic, tricyclic. It just depends on the compound. All right. It needs to be planar so that the orbitals can all overlap, and that planarity and the fully conjugated criteria go together, right? Because if it's planar and all the p orbitals can overlap, and there's a p orbital on every carbon, then the conjugation is not going to be an issue. and then it has to meet the Huckel rule, the 4n+2 rule, right? So you set the number of pi electrons equal to 4n+2 and solve for n. If n is a whole number, then that rule is satisfied. So those are your 4 criteria for aromaticity. So let's look at a couple of other examples. Cut this out. Let me add another page here. All right, so these examples, we've already talked about benzene, right? Let's look at naphthalene and see if it matches. So I'm going to draw this, just redraw it. So this is naphthalene. If you have grandparents that are over 70, you may have gone to their house to smell that peppermint, almost like a mint type smell in the closet. That's from mothballs. This used to be the principal component in mothballs, right? It's got a really pungent, minty odor to it, and apparently it works. I think nowadays the moths are not as big of a problem as they used to be, but apparently it used to be a big deal. Everybody would just put mothballs in the closet around their clothes to keep the moths from eating the fabric. But now with all these synthetic fabrics, I don't think that's a problem. So with naphthalene, let's see if it matches. So is it cyclic?
Yes.
Yes.
It just happens to be 2 rings fused together, but it is still cyclic, right? Is it fully conjugated? Let's ask that question. And the way you figure that out, if you can't just eyeball it, right, is to go ahead and put your p orbitals in on each carbon. Right? Does that satisfy the full conjugation?
Yes.
Mm-hmm. And the fact that those carbons are sp2 right here, where the 2 rings come together, that's going to ensure that it's planar, because that bond angle is going to be 120 degrees, and there's not much deviation from that. Even with it being bicyclic, it's a very rigid structure. All right. So it's fully conjugated, it's planar, it's cyclic. Now we need to figure out if it meets the Huckel rule. Right. So how many pi electrons are in there? How many double bonds are there? Let's start there. We just take the number of double bonds and multiply by 2. 5 double bonds. So that means you have 10 pi electrons. So in this case, n would be what? 2.
2.
All right.
Mm-hmm.
That's a whole number. So it satisfies the Huckel rule. So with that, this compound will be considered an aromatic. Right, satisfies all the criteria. All right. So let's look at the ions that are here, because these are special cases, right? Both of these are special cases. So let me start with the cyclopentadiene. structure, which is here. Now, if we were to look at this structure, I'm gonna put the hydrogens in here too, because that's how we're gonna make it into our, and we're gonna do a proton transfer and deprotonate it. Right, but if I looked at this structure, right? How many of those criteria do you think it meets? We can see that it's flat, it's planar. We can see that it's cyclic. Is it fully conjugated?
No.
Oh, right, because this carbon is excluded. There's no p orbital on it, so those p orbitals can't overlap. So it's not fully conjugated. All right, and then it's also doesn't meet the Huckel rule. Right, because if you took that 4n plus 2 equals 4, n would be 1/2. Is that right?
Yes.
Yes.
So we can't say that that's aromatic. But if we treat it with a strong base, like potassium terbutoxide or something like that, right, we could actually pull off one of these protons. That proton has a pKa somewhere about 15 or 16. Somewhere up in there. So it's about the same pKa as a alcohol proton. So a good base, you can remove it. And let me just show that real quick. I'm just going to abbreviate the base as B. Bring that in there and do a proton transfer to the base, right? So what I end up with now is what we call the cyclopentadienyl anion. Cyclo because it's a ring, penta because it has 5 carbons in the ring, diene because it has 2 alkenes in the ring, and then the ill part because now it's a anion. Right? I need to fix that, sorry. Nice going, Russell. All right. So now let's look at it now and think about it. It's still planar. No problem with that. Right? It's still cyclic. That nothing changed with that. The question now is about the conjugation. So when you see that anion, right, if we were to draw that out and show the orbitals, right, that negative charge, those that pair of electrons is in a p orbital. So that's what my negative charge is coming from. Right, and then here, those are still there. So now, is it fully conjugated?
Yes.
It is, right? There's a p orbital on every carbon. And does it meet the Huckel rule now? Because that pair of electrons in that orbital now contributes to the overall number of pi electrons, right? So if you got a pi electron and both 2 pi electrons in each double bond, plus 2 in the orbital where the anion is, then 4n plus 2 is now what? 6 instead of 4. Is that right?
Yes.
Yeah. So the lone pair is 2, and then it's 2 in each pi bond. So you have a total of 6 pi electrons. So now you can see that it meets the Huckel rule. So the cyclopentadienyl anion is aromatic, even though cyclopentadiene itself is not. All right. I think with the other, and I'll just hold off on that until Monday, but we can look at this system real quick. So this is a 10 pi system. You got 1, 2, 3, 4, 5 pi bonds. But the fact that it is a 10 pi system, but it's in a ring that is a, let me see, 1, 2. So a 10 member ring. When you get past like 8 carbons in a chain, those rings start flexing and contorting and experiencing what you call transannular effects. So when those rings start doing that, the planarity gets broken up, right? Because they start flexing and moving around for stability. So if we look at the p orbitals here, and it might meet all the other criteria, but the fact that these p orbitals down here are perpendicular to the other p orbitals that are up here, they can't overlap. Right, so these p orbitals right, they're perpendicular to the pi system. So that breaks up the conjugation and it breaks up the planarity, right? And so a molecule like this, where it's a 10 carbon ring, and it's a pentaene, is not going to be aromatic, right? That you can't get the right overlap for it to be planar and for it to be fully conjugated. So we're going to stop here. We'll pick up on Monday. We're going to look at this cyclopentadiene cation. And then we're also going to look at some reactions that aromatics do. Because again, benzene doesn't react unless it's in the presence of some type of catalyst. So we'll pick that up on Monday. Any questions about anything that we've talked about? So really, this handout and this on Blackboard, it's in the aromatics folder. This is a short section, right? We're going to talk about these reactions. We're going to talk about directing effects, and we're going to talk about a little bit of nomenclature with benzene rings that are disubstituted, and then we'll be moving on to spectroscopy. So NMR, infrared, UV, and mass spec. All right, so we're going to stop here and we'll pick up on Monday.
Thank you. Have a good weekend.
All right, y'all too.